Sorry for that. So thank you. Hello, everyone. I am Maricel Gonzales, a PhD student at the University of Georgia, and today I am presenting our study on the integration of wild Arachis cardenasii Alleles into cultivated peanut to confer resistance to early and late leaf spot. So early leaf spot, or ELS, is caused by the fungus Passalar arachidicula with this a brown lesion with a yellow halo that produces spores on top of the leaves, and late leaf spot is caused by Notopassalar personata with darker lesions and produce spores underside of the leaves. So they are the two of the major constraints in peanut production, and they could cause up to 80% yield loss when not properly managed, and they could occur as a disease complex or as one distinct disease, depending on the prevalent fungus in a given area or a given year. One of these two diseases is enough to cause tremendous yield, and the total loss in 2018 in Georgia was estimated up to $42.7 million. So these diseases can be managed by cultural practices that could only delay symptom appearance and could be effectively managed by using multiple fungicide program on large-scale farms, but it is very costly.
Maricel, I'm going to stop you just for a second. You've gone off of the presentation mode. Can you try to get back to that? I think it'd be better. We're reading your notes as you go through right now. So if you can try there, if you can stay on that, that's great. And your audio is a little bit broken, so you might want to turn your camera off to make it a little bit clearer.
Okay, so
perfect.
I'll just continue with this slide. So leaf spot disease can be managed by cultural practices, but it can only delay symptom appearance, and they can be effectively managed by multiple fungicide program, but this is very costly, especially on small scale farms. So the use of resistant varieties is the most practical way to mitigate leaf spot diseases by minimizing the production input, but the cultivated peanut that we have doesn't have a high level of disease resistance. Sources of resistance have been identified in wild relatives of peanuts, and these wild species can be utilized for crop improvement. So an example is the use of Arachis cardenasii to confer disease resistance, wherein Arachis cardenasii that originated in Bolivia was used in the US in multiple breeding programs that resulted to the release of multiple resistant lines, and it is continuously used around the world in breeding programs to for crop improvement to confer disease resistance. And in the US, none has resistance to both ELS and LLS. So these are our objectives: to obtain lines with multiple resistances that combine wild-derived chromosome segments from Arachis cardenasii and to evaluate their resistance to ELS and LLS. And we hypothesize that combined wild resistance alleles will provide high level of resistance to ELS and LLS. And our overall goal is to develop advanced lines with multiple resistances from wild-derived segments that can provide long-term high level of resistance to foliar diseases. To combine the wild-derived chromosome segments, I use Bailey and IAC 321. So Bailey is a Virginia type peanut with resistance to various diseases, including ELS, but it is susceptible to LLS. And IAC 321 is an advanced line in Brazil and has resistance to LLS and ROS, but it is susceptible to ELS. Both of them have introgressions from Arachis cardenasii, shown by the red and the green segments. Bailey has a longer introgression in the AO2 chromosome than IAC 321, And it also has an introgression in the AO8 chromosome. And IAC321 has an introgression in the AO3 chromosome. So our goal is to combine all these segments and combine all the resistances that they have. So here's an overview of our breeding experiment. And to look closely, I cross Bailey and IAC321. And then we identify hybrids using the KASP assay. So this is an assay that uses DNA markers that identify the parents and the hybrid. So after identifying the hybrid, I cross it back to Bailey. And then we see the segregation of alleles in the BC1F1s. So some of them only have segments from Bailey as shown by the red bars. And some of them have both integrations from Bailey and IAC321 as shown by the red bar. So we confirm the hybrids and then use some of them to evaluate for ELS and LLS. We also use TifNV H and cross it to the F1 hybrid with the resistant segments to the foliar diseases. And TifNV H is a runner type peanut with resistance to root knot nematodes and a high oleic trait. And it also has an introgression from Arachis cardenasii in the AO9 chromosome. So to evaluate the ELS and LLS, I use the detached leaf bioassay because it requires minimal amount of inoculum, leaf tissue, and workspace. And more importantly, in evaluating hybrids, it allows multiple replication from one plant. So in this assay, we placed leaflets on top of a glass slide, filter paper, and a cotton pad, and then inoculated it with the standardized 10 to the 5th spore suspension using a paintbrush, and incubated them in the dark for 48 hours at 25 to 27 degrees Celsius to promote spore germination and fungal infection, and then arranged them in a randomized complete block design with 6 replicates in a growth chamber, with a photo period of 12 hours light and 12 hours darkness at 25 to 27 degrees Celsius. So we maintain the moisture or the humidity on each petri dish by watering the filter paper and the cotton pad every other day. I use the following plant materials. I use 4 BC1F1 from the hybrid from the Bailey crosses and 3 from the TifNV crosses. All of them have the segments from the AO3 chromosome and AO8 chromosome, and also the segments in the AO2 chromosome, except for one TifNV hybrid cross. It doesn't have any segment in the AO2 chromosome. I used runner 886 as susceptible control and the parents, and also some of the cultivated peanut as controls. So experiments were repeated twice and results were consistent on both experiments. Due to the time constraint, I will be only presenting one of each bioassay. We measured 6 different components. This is resistance components, but I will mainly focus on the last 3 because they are the best metrics to measure the disease resistance. So for the number of sporulating lesions, the sporulating lesions estimates or measures the production of secondary inoculum or spores that could start new infection in the field. So more sporulating lesions means there will be more spores that could spread in the field. So in the ELS bioassay, 3 hybrids have significantly lower sporulating lesions than the susceptible parents, TifNV H and IAC321. Same with the LLS bioassay. Most of the hybrids have significantly lower sporulating lesions than the susceptible parents, Bailey and TifNV H. So we also measured the AUDPC, or the area under the disease progress curve, it is a quantitative summary of the disease intensity over time, or the total amount of disease over time. So higher AUDPC means also more disease. In the ELS bioassay, again, 3 of the hybrids have significantly lower AUDPC than the parents, TifNV Alleles and IC321. Same with the LLS bioassay, wherein most of the hybrids have lower AUDPC than the susceptible parents, TifNV Alleles and Bailey. So we also measured the AUDPC of the sporulating lesions, and same results were obtained as the last one, wherein the hybrids have lower AUDPC values than the susceptible parents. So to look at the disease progress, the hybrids have slower lesion development as compared to the susceptible parents. Also same with the LS bioassay, but except for one hybrid. This is the TifNV S20, wherein this genotype doesn't have an introgression in the AO2 chromosome, unlike on the other hybrids which has introgression in the AO2 chromosomes. So based on the sporulating lesion, again, the hybrids in the ELS have slower sporulation rate, and also in the LS bioassay, and it can be noted that although the TifNV C20 has a faster lesion development, it has a slower sporulating rate. So this suggests that hybrids produce less spores than the susceptible parents. So here are some of the leaves that I use in the bioassay, where you can see the hybrids have lesser and smaller lesions than the susceptible parent IAC321 and TifNV Alleles. And here are some of the leaves in the LS bioassay. Again, they have lesser and smaller lesions than the susceptible parents Bailey and TifNV Alleles. Here you can see a lot of lesions in the TifNV hybrid S20, but only few of these lesions are sporulating, unlike the Bailey and the TifNV Alleles. So results of this study suggest that the obtained hybrids with wild-derived segments from Arachis cardenasii confer resistance to both ELS and LLS, and hybrids have lesser and smaller lesions with few sporulation. That suggests that there will be less secondary inoculum or less spores in the field that could spread and start new infection, and thus less fungicide spray will be needed. And also hybrids have lower AUDPC values or lower disease, and they have slower disease progress. We can conclude that hybrids with the combined wild segments perform better than their parents. And by combining the different wild-derived segments, we also combine the different disease resistances. So currently, I am evaluating the BC1F2s to ELS, and I will also evaluate them for LLS and rust resistance. And we also planted some of the BC1F2s in the field in 3 different locations with different disease pressures. And we are also incorporating the wild segments with foliar disease resistances into top breeding lines and in a very popular peanut variety, the Georgia 06. With that, I would like to thank my committee, members of our lab, and the student workers. And this ends my presentation, and thank you for listening.
Thank you very much, Maricel. We have time for questions. The first question comes from, and you can probably turn your camera back on. The question comes from Dr. David Langston. How did you measure the area of sporulating lesions?
I didn't measure the area of the sporulating lesions. I only counted the number of sporulating lesions.
All right. Any more questions for Maricel? What is the time frame that you expect before the breeding lines you have might be put into a commercial cultivar, or a cultivar that could be tested for commercial release?
So after we identify the best combination of the segments, then we can fix that into a variety like Georgia 06G, and then using DNA markers like it will take only few crosses, maybe up to 3 back crossing, so maybe 3 years or 4 years, and depending on the regulations here on how to release the varieties.
Okay, thank you. And that's the time we have for the presentation. Thank you very much, Maricel, for participating today.